Hello guys, welcome back to the channel, and in this video I wanted to address the lack of popularization basically that we have with the field of condensed matter physics. Before we jump into this topic, if you guys are new here, welcome to the channel. This is typically a bookish channel and a science and math channel, so if any of the two topics kind of pique your curiosity and you took a look in the channel and you like what you see, then feel free to hit the subscribe button, and if you like this video, hit the like button. It helps for people that are curious about this content to reach it through the algorithm. But without further ado, let's continue with the topic. So, in principle, we see that a lot of times when looking at science communication efforts, it's oftentimes from fields that are much more, you could say, at first glance attractive to people. It would be things like astronomy, astrophysics, and particle physics. These are typically the fields which come to the eyes of even, you could say, the layman audience and people that are not aspiring to be physicists but want to pick up something to learn about when it comes to physics. And I find it quite interesting that these fields are typically the ones that are presented first, and while there are so many other fields in physics. So I was thinking about this, and even though I myself personally, my field of interest is in a particular branch of astrophysics, which is cosmology, I still have a very open mind. I want to learn about as much as I can about so many other fields. Whether or not I want to do projects in them, I just still feel like it's important to learn about everything that is out there as best as I can, at least. So I was curious when learning about condensed matter and solid state physics and seeing that in practice it is technically one of the biggest fields out there in physics, that it doesn't have as much spotlight. So that kind of got me thinking, and it's also the reason why I'm making this video, because the more I tried for myself to learn about condensed matter, I noticed the much harder it was to actually get good content compared to if I was looking up something about the fields I've mentioned previously. I will say I saw that there are some things out there. For example, PBS Spacetime has some nice videos that are condensed matter related, and there's this really nice short video about this professor that makes a really funny analogy comparing condensed matter to other fields, but I thought that it was rich and great as well. And there is this much more lengthier, you could say, video that is an interview with Philip Anderson, a figure which I will be talking about this experience and his life and how he made certain contributions that are very important and big in condensed matter physics, and actually that even has tie-ins to other fields. So there are things out there, but for example, there's not as much stuff like, for example, the channel, PBS Spacetime falls into this category, but it's the only one that I found. But there's not stuff, for example, like the channel Science Click English, which if you've seen this channel before, it has amazing animations on the topic of general relativity, quantum field theory, and things regarding pushing basically the lines of high energy theory like string theory and such. And I was wishing there was something like this, and perhaps there is, and I didn't know of it. And if you know of it, please let me know in the comments down below. I'm desperately looking for something like this for condensed matter, but I haven't found it yet. And the stuff that I do find, besides PBS Spacetime and some of the others I've mentioned, are highly technical, like their lectures or their conference videos, which again is great because you get a feel of what the thing actually entails, but you would hope for there to be something which is the middle way between approachable for, say, an undergrad and highly technical. Like, for example, there are one that I didn't mention, but that is, I think, was the best example was, for example, the podcast channel, the Icon Bros, which unfortunately I don't think they're making videos anymore, but it was and still is one of my favorite podcast channels on physics. Like, these two guys were very informal, hilarious, and made really good videos about certain specific topics in physics, and they made some podcasts about quantum information, about the quantum Hall effect and things like this, which are relevant for condensed matter and superconductivity and stuff like that, because both of them were condensed matter physicists, experimentalists, but unfortunately I haven't found something like that ever since. And some of the podcast channels which I do think are really great, like Sean Carroll's Mindscape podcast or this podcast channel called Theories of Everything, I think all of these are great, but they're all focused on high energy theories. Of course, theories of everything, the thing is given in the name of the channel, so I guess that I should know what I walk into. But for such high quality, like his videos are great and really high in quality, there isn't a lot of things beyond that topic, you know? And that's the thing which I find unfortunate. I wish there was something at his level of quality and in the level of Sean Carroll, but that covered most other areas of physics as well. I mean, that's hard to ask. That's a hard ask because one host can only do as much background research and reading to convincingly ask questions to professionals. But maybe I guess what I'm asking for is something akin of Lex Friedman, but it is even more physics focused because Lex Friedman does a wonderful job at this, at navigating different fields as well as basically trying to create this content that is somewhat technical but still approachable. I'm asking basically something like that, but with a flair of theories of everything or with a flair of the Eigenbros. So if something like this were to happen, which I am going to make more words about at the end of this video, that would be great. But since we don't have that, I was thinking, why is it that we don't have such content in condensed matter physics? And I got to think of this, and I got through many, many ideas and theories, you could say, but the one that stuck out to me the most, which isn't an original thought, but is one that I think is, in my head at least, seems the most logical for why some people in the community of condensed matter do not worry too much with, you could say, the popularization aspect of their field. And the thing that I'm suspecting is that, in principle, because when securing grants and such, whether it be for experiment or theory, people in the field of condensed matter physics typically have a much less difficult time, it seems at least, to tie in the relevance of their research to something else, like to say why it is important, their impact. It seems like stating the impact when it comes to condensed matter physics, even if it's in an area that is a bit more abstract, it can still be done with less, you could say, hand waving compared to other fields, where, for example, if it's particle physics, when you try to invest in these big experimental colliders and such, then typically these are very, very large scales, demands a lot of money, and typically from the trends that I've noticed, the main key point of them trying to get the grant isn't usually for the impact the science has directly on society, because typically with particle physics and other areas of fundamental research like astrophysics and such, the impact isn't direct. You can always state that there will be spin-offs, and this is of course indeed true, but you don't have a crystal ball to see what these spin-offs will be. So typically the thing that I've noticed that scientists in these areas kind of hammer on is the prospect of there being, for example, a good prospect for employment. For example, if you're creating a large-scale international collaboration, then that's going to be great for the nation. You're going to contribute in an at least significant manner to the capita, and you're going to ensure that there will be people from all around the world who will be interested in coming to your, you could say, institute, because it's going to be a hub for doing this experimental technique, because it's going to be one of the few places in the world that will be doing this experimental technique. So what I'm stating is pretty much things, for example, like experiments at CERN, or even in the US with Fermilab, or even in Japan with some of the big experiments they have for things regarding astroparticle physics or just particle physics in general. But you can see that that takes quite a lot of communication effort from scientists in this field, and I feel like that is the skill that they utilize not just in their grant writing and communicating with government officials, but also, or sponsors, but also when communicating with the public, because at the end of the day, the money a lot of times, besides certain, you could say, industries and such and government, it comes from taxpayer money, especially if it's government, which is a big portion of where scientists typically get their funding. So you want to convince the public that the research you're doing is significant. So by that means, if it's this very abstract fundamental thing, then the way you get to do that is by doing popularization, doing basically what I would personally say Carl Sagan started out, like stating the meaning as to why we need to learn about the stars, why we need to care about trying to find life out there and things like that. Carl Sagan, basically one of my favorite science communicators of all time, He was one of the key proponents of doing this, and many more followed him, especially in the field of astrophysics, which I think they've done beautifully. Continue to do that balancing act of both research and doing science communicating. And I mean, if you go now on Instagram or TikTok, I'm not on TikTok, but I'm sure if you go on TikTok and just on YouTube in general, you see that many students, even in their undergrad, myself included, honestly, try to do this like communication type of effort thing because one, it makes you kind of feel like you're giving out to the community, at least in a very small way, while also allowing you to train yourself in communicating these hard concepts in as much of a straightforward narrative as possible, because that is important. I think when you're trying to communicate with an audience, and this is going to tie directly into my point about condensed matter people, you want them to understand what the hell you're saying. You want them to understand what you're working on, even if that means smudging the details a little bit. I've spoken with a friend of mine recently, and I say that science communication kind of has this Heisenberg uncertainty relation thing going on between abstractness of the information you're communicating and precision of the information you're communicating. It's like when you're abstracting the details, you're able to perhaps provide more clarity about what you're doing by not being as precise about the details and technical jargon, but of course you lose depth. You can even give sometimes people the false sense of them feeling like they know like a thing or two about a given topic and making these some false assumptions, and whereas no, they don't know some of the nuanced details about the problem you're working on. This is a lot of times where emails come into, especially people in these fields particularly, they get emails a lot of times from people saying that, aha, I have my theories about why supernovae blow this particular way, or aha, I have my theories about black holes, or aha, I have my own theory of everything. So this is where it kind of comes in, because science communicators in these fields does honestly their job a bit too well, that people in the like in layman basically kind of get the feeling that they can kind of do the same thing that scientists are doing without being aware of how technical the work actually is. And the other side of this uncertainty principle, as I like to call it, is the precision, where you're very precise but then alienating basically so many people from your field because they don't have the know-how to understand what you're talking about to begin with, such that a lot of people don't know the relevance and why you should be excited about this thing you're working on. Even though people in your field, of course, will pick it up, but even then, so with a little bit of difficulty. So this is a thing which I think is a problem in condensed matter, that a lot of times when I see some people trying to communicate their efforts with things, try ways and ways I've mentioned before, like with videos, especially if you look them up, it's a lot of times lecture videos or conference videos. So these are, of course, by nature very precise because they're meant for grad students or undergrads, or they're meant for professionals who are kind of wanting to stay in touch with state-of-the-art development. So it is very hard to see a thing which kind of shows you from basics to like a nice superficial but detailed understanding as to what is going on there. I mean, the closest I found to this was this lecture. I think it's something called the Oppenheimer lecture, because it's held at UC Berkeley, and it's like this annual tradition given by this professor. I'll just put the picture of that here. It's a lengthy video, but this was done with the intent of introducing everyone as to what the building blocks are of solid state physics from history to what are some of the open problems now. And I did think he did one of the most accurate jobs with it, besides that guy with a very funny analogy, which I've talked about earlier, but I will show the picture of again. Like, that video is hilarious, much shorter, but also does the same trick. But what I wish would happen is that I wish we would have more content that does this. I wish we would have more things like podcasts, like animation channels that are able to kind of do the same level of science communication as we get with fields that I've mentioned before. I mean, there's one aspect of condensed matter that does do this already, and that is actually the area of quantum computing, which is a big area that is actually pretty much a subcategory of condensed matter physics. And that is the one that has, you could say, a lot of traction and a lot of attention because it's quite interesting for both laymen, because it's something with quantum, which always piques the curiosity of people, but also it's one of the things which basically it's apparent possible use use is very clear to the audience, because again, the communication I think has been done very well on this side as well, to show that okay, with quantum technology you can do things quite more efficiently than you could with classical computers or with classical means of other types of technology. So I do think that is an area where the communication has been done pretty well. But there are so many other interesting problems in condensed matter, and I'm saying this even though, again, being someone that is pretty steadfast on going into cosmology, for example, again, even though with my open mind and learning about other things, I do think there are so many interesting problems in condensed matter. And recently, the thing that got me thinking more about this is that I started reading this book, A Mind Over Matter by Andrew Zangwill, who is an author who wrote many great textbooks from what I heard as well. But he wrote this biography about Philip Anderson, who was a prominent figure in condensed matter research. I'm reading about it right now, and it's such an enthralling read that even though it's about 400 pages or something, I'm already almost reaching, like, I would think I will reach halfway there by tonight or something, because it's such a great read. Strongly recommend this book, no matter what field you're in. If you're an undergrad in physics or just someone who's curious about physics in general, I would recommend it, because it did basically what the book Higgs, which is somewhere on this shelf, it did what the book Higgs by Jim Baggott did for me, to introduce particle physics, its history, and where we are now very efficiently. It did that, but for condensed matter. So in that same spirit, it does have some technical lingo, but no equation, good figures and everything. But it does help if you're comfortable with at least a little bit of physics, especially for this one, like when you start talking about electricity, magnetism, which is a big aspect of condensed matter, then you definitely would want to be a bit comfortable. But again, you don't have to have taken a course or anything. You can quickly Google stuff if you don't know something. But this book, besides introducing you to this interesting person that was Philip Anderson, it uses Philip Anderson's life to delve into condensed matter, to delve into the history and developments in condensed matter. And for example, one of the most beautiful things that I learned about from this was the thing which I think is the thing that Anderson won the Nobel Prize for, but I might want to fact check myself. But regardless, one of the big things that he contributed at was this concept of spontaneous symmetry breaking, which he didn't coin that when he developed his theory, but it was for this notion which you have a material and you have them be in a particular polarization. It was a material filled with ions and ions of different types, and they would have their, you could say, polarization, their magnetic moment, you could say, pointed in a particular direction. And he wanted basically to coin a framework, a theory, at which kind of states what happens when you get this material to be a certain type of, in a particular type of state called antiferromagnetic. And to sharply define how basically this material will become antiferromagnetic, just think of it as a fancy way of the, you could say, polarizations or the spin of this material being aligned in a particular way, very orderly. For this to happen, he used the concept of symmetry from group theory, and it becomes quite interesting, where basically the general properties of this material changes completely at a given point because of something called the symmetry breaking. And the same concept was later used by Higgs and I think Engelhardt, I think I might butcher I've butchered the name likely, I will correct myself, to propose the Higgs mechanism, which, as you might know, is the thing that describes how through some symmetry breaking process in the case of particle physics of this Higgs field, particles that are typically described in the Standard Model, especially these things called bosons, they acquire their mass, especially in the case of the weakly interacting particles. And that describes why they are so weak and also why they are so short range. So this fascinating concept of symmetry breaking was actually borrowed from Anderson's insight in condensed matter systems, and this was a trend that continued to happen. And there are so many interesting things, both on the theoretical and experimental side of condensed matter, that both, I think, could intrigue the most curious of physics people and just people out there in general. And I think some of the areas in general which are quite interesting are things like ultra-cold atom physics, so looking what happens when you cool things down very much. For example, experimentally, this would be using lasers of a very specific frequency shooting it at a particular substance, and the atoms in the substance, basically the nuclei, would start oscillating less and less and less to the point at which you can get them to be so cool at which quantum mechanical effects become relevant. You can do this. You can do a technique of cooling things down as well to study superfluids, which were studied even back in the 40s and 50s, with even Feynman having worked on superfluid helium for some time. And there's also another area which is very interesting, that is basically something called topological materials, and it is being this very specific configuration of a material at which electric conductivity happens in it. So by rearranging a material somehow, you can get, for example, that the surface of the material becomes conducting, but the bulk of the thing acts as an insulator. Now you can picture that this can have many practical applications as well as a lot of place for playing, basically, when it comes to model making and theory. But of course, one of the crown jewels of condensed matter, one of the big problems that everybody, of course, is very curious to work on, is superconductivity. And that is where you have materials which their resistivity is lowered so much at a certain, you could say, given temperature and given pressure conditions, that current can flow freely, basically, without any sort of resistance. This would have major commercial, like you could say, impact if it were to be scaled to room temperature and low pressure. So basically a circumstance at which it's much more cheaper to maintain, such that you can have grid lines and public communication systems which would work much more efficiently. And superconductivity is a rich thing both experimentally and theoretically. Experimentally, the thing started out even in the late 1920s with the discovery of the first type of superconductor in Leiden in the Netherlands by Kamerlingh Onnes and his students. Just by adding, I think, liquid helium or something like that, they were able to cool down a material and just test its resistivity with currents and see how the thing just dropped, basically pretty much to zero at a given temperature. People were bamboozled, and theories didn't exist back then to explain it very well. But then came Landau and I think Ginzburg, and they came up with this very phenomenological theory for conductivity of type 1 superconductors. Phenomenology just implies that they looked at the data and found something that could roughly, you could say, predict this macroscopic property of superconductivity. Pretty much the same thing thermodynamics is when describing heat flow. It doesn't care about the microscopic things that are happening with substances, but it can generally describe how heat would flow from one thing to another, how it would affect things like entropy, pressure, volume, and all of those other things. While the microscopic description of these same things would be, in the case of thermodynamics, statistical mechanics. That would describe how ensembles of particles would behave, how that gives rise to temperatures, entropy, and all of these things. Now, the equivalent of that came a bit much later, but at the same time is such a beautiful theory, is the Bardeen, Cooper, and Sheldon, I think, BCS theory, which again, I will correct myself for the full names down here, but that used this concept of Cooper pairing to describe how superconductivity would work. Now, an equivalent for that does not exist for describing high temperature superconductors, which experimentalists at least know there to be some of these candidates, but there just isn't a theoretical framework. So that's a place where a lot of theorists are hammering at the problem, and they're hammering at it from what I understand for now at least, through either techniques from quantum field theory, so something called many-body physics, so it uses some of the same techniques of Green's functions, propagators, and all of these techniques which someone typically sees in a quantum field theory class, especially techniques of renormalization group flow to try to model behaviors of superconductors, and also same goes for topological materials, to hopefully make some predictions about how one can build materials with specific, you could say, inputs, specific dopings, as one would say in jargon, so specific elements and ions, to give it hopefully these properties, and you can then try and synthesize them in a lab and hope to see if that gives you the thing you were hoping for. So the beauty of this is that you get to, for example, if you're someone who's very theory oriented, you get to use these techniques you learn in a quantum field theory or a statistical field theory or a condensed matter field theory, however the university would call it, class, and you can directly make things you can test for. Like you can directly do phenomenology with it, which depending on which type of theory person you are, it might appeal to you very strongly. Like if you're someone who is more of a phenomenology person, you like to work with theory, but what it work closely with what it tells you about experiment, then this might greatly appeal to you. And that is less often the case, especially I noticed in high energy theory, where, for example, the main bulk of using quantum field theory there, or the closest thing to the main phenomenology there, is that you calculate these things called scattering amplitudes, which tells you the probability of a certain type of decay mode or transition happening in these collision experiments. And these are great, but especially when you could say, calculations that you're making become more, where you make more assumptions, or where there are more uncertainties in a particular thing you're integrated over, or whatever you have, then there's more room for uncertainty, because one can simply argue that the detectors didn't pick out some resonance or something that you were looking for, because it was just outside of the sensibility of our given detectors for the experiment. So that's where it becomes a bit, you could say, more tricky and iffy. And I'm sure problems of this nature exist in condensed matter as well, but it's basically a lot of times you can do a lot more tabletop experiments to test your theory, compared to a lot of times in the case of high energy, where you need big collaborative experiments. So that is one thing. And another thing is that even if you're more of the other hand of things, so instead of being more phenomenology oriented, you're the theory student who is more, very much more focused on pure theory. And if you happen to like some of the methods, from what I heard, that people in string theory use, which typically right now is particularly doing dualities, like doing all of these holography calculations where you're working in one, you could say, framework, one bulk model, and map it on basically to another. By solving your problem or scattering amplitude or what have you in a given situation, you could say, map it onto the other thing. You can use similar techniques in condensed matter, from what it seems, and it's becoming an increasingly popular thing to do. Now, to what success, it tells you something about experiments that I'm not sure of, and this entire field I am not quite sure of, but I can talk a little bit about it because it's the one I've looked the most into, compared to, honestly, some of the experimental frontiers. So for experiment, I'm sorry, I can't say much, unfortunately. But yeah, a lot of work is being done on this end for pure theory. So if you're still someone who likes the mathematical framework and techniques there, or you think you might be one of those people, then I think you still have a place in condensed matter. But with all of that, I wanted to state that the physics of emergent things, like emergent properties of materials, can be as interesting as studying the very small or the very large scale and astrophysical, and oftentimes we surprisingly use the same techniques as in both cases, both either mathematically or experimentally with detector building and sensors and such. So I do think this field really warrants the interest of anyone who's curious to learn about the physics of stuff around us, the physics of why glass is a certain way, or the physics of how, for example, how magnets work, and all of these things which could be very interestingly explained or studied carefully through condensed matter physics. By the way, even though I talked about metals and such, condensed matter stretches all the way out. Like, for example, I talked a bit about quantum information, which already is pretty much branching more closely to information theory and computer science, but condensed matter also branches out to, for example, biophysics. For example, I went to a conference, I think last week or late 2 years ago. I think no, it was 2 years ago. Damn, time flies. But I went to this conference in Delft in the Netherlands, where there were some of these R&Ds, and there were some people working there on biophysics. And I went to these talks because I know the least about this area, so I kind of wanted to hear about it. And it's fascinating stuff. By looking at, for example, the embryonic development stage of like how you could say tissue kind of rearranges itself in embryos in their early developmental stage. Some physicists were able to model this, you could say, the patterns at least, through statistical mechanics, and try to imply that for certain, I think they're called smart technologies or something like that, some type of technology at which basically could fold in a particular way to kind of reduce stress on it, and it can go back into the shape it had originally just by the way at which you make the polymers from which these materials were made of. And these things, of course, can have both implications when it comes to basic research, so fundamental research, to try to learn at how polymer chains kind of arrange themselves and study the statistical mechanics of that. And of course, learn more about how tissues themselves kind of behave in human bodies, because that is a great enigma, the physics behind that at least. But also have implications, immediate implications, like being able to make better materials is especially handy for making better implants, for example, for therapeutic reasons in clinics and hospitals. So you can see the relevance of this creeping up there. And even in these very high energy scenarios, you can think about the usefulness of condensed matter. At CERN, for example, I made this big videos about when I went to CERN, but at CERN, making superconductors is important, of course, for accelerator physics, so for making strong magnetic fields to concentrate the beams that go in these large detectors. But also, one thing I learned about recently, which is fascinating, is creating analog systems. So this is going more or less into quantum simulation territory. So trying to mimic something like, for example, black holes by ensuring that, for example, if you have a material, something like graphene or some other 2D material stacked on top of each other, by placing some charges and things in a particular way and make sure that it's like superconducting, so very low temperature, so that you have those quantum behaviors that you want, by creating a region that acts in a lot of ways, like for example the event horizon of a black hole. You can try to look for, in a condensed matter system at least, for these things which would be akin to something like Hawking radiation. A very interesting thing has been done, I think, earlier this year, where they did this to try to model phase transitions in early universe. I think Sabina Hossenfelder made a really nice video about that, which I will place here. But you can see how analogs, quantum analogs, can help you study these more exotic phenomena without actually having to go there or make very clever and sensitive, you could say, telescopes and such. So for all of these things, I think this field of condensed matter can be equally as exciting, basically, as many of the other fields. And I hope more people see that. And I hope that this video motivates someone with creative ideas like Theories of Everything, like Eigenbros, and like all of these other podcasts and animation channels, Science Click English and what have you, to make more condensed matter physics stuff out there. There are definitely a lot of people watching these videos from high school already, so perhaps having such good content out there would make it feel less like, for example, honestly, like when people are in their undergrads, maybe entering grad school or something, that's where they start to maybe consider condensed matter. It would make it less jarring for them to think that it's a chore now. I have to give up my field of interest or whatever because I need to think more about what would be my prospects. Which again, none of us have a crystal ball, so we don't exactly know how any of these fields would evolve in a given span of time. Realistically, honestly, but still, it would make the choice of going to condensed matter feel less like a chore for some people, but more like, okay, this thing could be actually interesting. Maybe by reading again something like A Mind Over Matter, which I can't wait to review to you guys, or other stuff, other content which might be out there to their disposal. So I hope stuff like that is going to get done, and I look forward, honestly, to possibly seeing that happening, perhaps in a very, very hopefully near future. I hope you got something out of this video, either on condensed matter and what it is, as well as what I think the state of affair is and why we need good content out there. I hope one of you perhaps might be the person to make good content out there. So yeah, I will stay tuned for that myself now and just wait to see how this goes. Bye-bye, and in general, I hope to see you guys, of course, for other videos to come. Cheers.